Hey, I'm Bjorn Therese, and I'm here to introduce part 1 of my video series on process control. The approach I'm taking in this series is to teach process control by examples using dynamic simulations. These simulations are written in the programming language Swift, primarily so that they're easily converted to iPad apps. The app I'm using for this video is the Control Concepts app, and it's available for free on the App Store. There are 3 major aspects when approaching any control problem, namely the process understanding, open loop dynamics, and feedback control. In this video, we tackle process understanding and derive some useful information from steady-state calculations. Let's take a look at the opening screen of the Control Concepts app. To the right, we see the so-called piping and instrumentation diagram, or P&ID for short. On this diagram, there are 2 identical systems, but we're only going to be looking at the upper part of the P&ID. The process is very simple in that it tries to produce an exit stream of a certain temperature determined by the tank temperature controller, tank TC. We do this by augmenting a wild stream A with another heated stream B. So here's stream A, and here's the heated stream B. The wild stream comes in at the fixed rate of 45 liters per minute and has an average temperature of 50 C. Now this stream can also have fluctuations associated with it, so the average is 50, but it could be plus minus a certain number of degrees depending on the setting in the app. And this is useful in dynamic simulations in future videos. The heated stream comes in at 20 degrees centigrade and is heated by a heater that's capable of delivering 278 kilowatts of power. It's heated up to 50 degrees, and it has the same rate of 45 liters per minute as stream A. So both of the streams then are mixed at 50 degrees and therefore produce an output stream from the tank also at 50 degrees centigrade. And that, of course, has a rate of 90 liters per minute. The heated stream B, before it enters this tank, it goes through an ion exchange column that provides a process delay. The tank itself has a liquid volume of 2,000 liters, and it's at the outset of the simulation, it's 50% full, and this level is controlled by a level controller, LC1. Adjusts the output or outflow from the tank. The liquid volume and the ion exchange columns are, of course, necessary in this particular process, but they provide dynamic elements to the process, and we really don't need them to do a steady-state calculation. So let's focus on just the streams themselves and how they mix and come up with the exit temperature. What we'd like to find out from steady-state calculations is how much additional heat do we have to provide to the heater in order to raise the temperature of the exit stream from 50 degrees to, say, 60 degrees. In other words, we are heating up the exit stream by 10 degrees, but since the stream A comes in at 50 degrees, stream B must attain 70 degrees in order for the combined to be 60. So let's do the calculation to figure out how much additional heat we need. It's simple. We have 45 liters per minute, and we divide this by 60 seconds per minute to get the rate in kilos per second, and then we multiply by 4.3 kilojoules per kilogram and degree centigrade, and then we multiply by the 20 degrees centigrade that we need to raise the stream by, and that comes out to 64.5 kilowatts. So we can say that the steady-state gain, we'll call it Kp prime, it's going to be 10 degrees divided by 64.5, and that's equal to 0.155 degrees C per kilowatt, or Kp is equal to 10 over 100 divided by 64.5 divided by 278, and that is equal to 0.43% per percent. Now the 100 here, I'm assuming is the span of the temperature transmitter, so that normalizes the temperature. And the 278 was, of course, the total capability of the heater, so that normalizes the heat input, so we get 0.43% per percent. So it's a unitless gain, which is useful in control calculations. In a future video, we'll see how we can also determine the steady-state gain from an open-loop step test. However, these online step tests can be difficult to carry out, so it's very valuable to be able to determine process gain from, say, steady-state calculations. Oftentimes, you can use a steady-state simulator to determine some of these gains and relationships in the process. This concludes part 1 of the series, and in the next segment, we'll look at the open-loop dynamic aspects of the process.